Hi, I'm going to record myself trying last fall's final. So we also have staff walkthroughs for all of these exams. So if you try the problems and you're stuck on them and you want to listen to someone explain it to you, then I would definitely recommend those videos. I just make these videos because sometimes students tell me they like to hear about like my thought process when I'm trying them. So yeah, I'm going to try these problems um, fresh and then do my best to explain my raw thought process and how I think about these problems and how I get to the correct or the incorrect answer. In the video description, I'll list out any mistakes I make. So yeah, here we go. Um, it's 12:37, which means I get until 3:27. All right. So, and then, yeah, again, just a disclaimer. I will do my best to explain my thought process, but it's very unfiltered. So you might just hear me sit there and idle and think a little. Um, and I won't, um, I'm not really explaining an answer to you as much as I am just talking to myself. Um, all right. So number one is that what would Python do? For these, I tried to do very little, or for these, it should just, it's a very mechanical process, and I'm just applying the rules. So I like to just go with an environment diagram. Don't think, just draw the environment diagram. It's usually how I approach these, although I don't know if that's needed here. Um, so I'm gonna want to call, I'm gonna list out the output of calling this cut function on nums being this list. So I think it probably is helpful to have an environment diagram. So I have a global, I have a cut bound to a function, cut that takes s, parent is equal to global because those define equal. And then I have paste, same story. See? Um, and then I have this list. It's going to be called nums, and it's going to point to a list with the contents 0, 2, 4, 6, 8. Okay. So number one, we want to call this cut function on this list and then print out what happens. So, or list out what happens. Okay. So if I call it, I'm going to get a frame one. I'm going to copy down this signature. This tells me that the first thing my frame is S. I'm going to bind the formal parameter to the actual input being the nums. It's an object, so I'm going to point to that with a reference. And then now I'm executing code. This is equal to 1. I'm going to execute this for loop. For x in S. So, okay, first iteration, x is 0. I'm going to say if 0, which is not true. So I'm going to go to the else. This gets set to true instead. On my next iteration, x is 2. Um, now it's 2 is a truthy value. So I enter here, and then now I'm going to set this is equal to x, which is 2. And then I'm going to yield this. Oh, okay, so this is actually a generator. Um, okay, so in which case, when I call a generator function, although you wouldn't see this in Python tutor, actually, I would I kind of like to create this abstraction for what this calling a generator produces. A generator is going to yield a set of values, right? Like if I exhausted all the values out of a generator, then these would be the values that it produces. And I like to write them out here just for my own organization. So the first time someone calls next on this generator, the value they would get is this value we yield here, which is the 2. And then I'm going to do this and then list out all the values that this generator would yield over time. The next iteration, x is 4. So they're all going to land in this case because all of the remaining numbers are truthy. Is that true? Oh, sorry. In the last iteration, when x was 2, I didn't go in here because 2 is true, but because in the prior first iteration, we set this to true. So meaning in the second iteration, we enter and then this becomes 2, and then 2 is truthy. And then so if sorry, I misread this as if x, but it's actually if this. So now this is 2. So if 2, that's true, this gets set to x, which is currently 4. We're going to yield the 4. And then that, I think that will just go on. So now we have a series of non-zero numbers, which are all truthy, which will permit us into this if, and then we can ultimately yield that. Let me just consider what happens in the very last iteration. So in the very last iteration, or let me just finish this. So yield, this gets set to x, which is the 4. In the next iteration, if 4, that's true. But in the next iteration, we on the 6. So we're going to set this is equal to x, which is the 6, and we're going to yield the 6. And then on the final iteration, x is 8, and this is 6. 6 is truthy. This gets set to 8. We're going to yield the 8. Yeah. Oh, wait, no, I'm okay. So yeah, I completely misread this as if x. So on the first iteration, this is 1. So the very first value would yield is actually the 0. It would just yield all the zeros. Okay, all the values. So we never go into this case, basically. Because the value of this starts as a true value and it repeatedly gets set to true values. No, that is not true. Oh, getting already tripped up on number 1. Okay. So on the first iteration, this is 1. That permits us to go in. This gets set to x. So this becomes, so initially this is 1. And then it gets set to 0. And then we yield the 0. And then on the next iteration, 0 is not true. So we go into here and 0 becomes true. Nothing gets yielded. And then on the next iteration, this is now true. So we go in and this gets set to x. Okay, so on the, oh my God. I'm sorry, people. I'm really struggling on this for some reason. In the first iteration, we enter the if case, and we yield the value of x. On the second iteration, this has now become that first x, which is 0, which brings us into here. On this iteration, x is 2, so it seems like the 2 has been skipped. On the third iteration, x is now 4. If this, we skip the 2, but this is true, so we go in here. This is equal to the x, which is 4, and we yield the 4. And then I think from then on forward, they will all be truthy. So in the next iteration, this will be 6. And then if 4, then we go in here, and this gets set to the 6, and then we yield the 6. And I think it works like that. Okay, I'm going to list, cut, map, lambda. I'm going to map subtract 4 onto a call of cut nums. Okay, so cut nums returns a generator, which is an iterator, which is an iterable, which allows me to map a function onto it. So this is the set of values that cut nums would generate. Generates this. And then for each of those values, I'm going to map subtract 4. So that would produce this set of values. And then I'm going to call cut on it again. And that works. It seems that cut is not making any assumptions about what type that input is, except that it's iterable. We just for loop through it, and we can loop through any iterable, but it doesn't, force it to be a list or anything. So it's totally okay to pass in what we are passing in here, which is a map object. And a map object is iterable, and we're going to for loop through it. So yeah, now we're going to call cut on this iterable. So let's think about what will happen in that case. Right. So if instead the input iterable is -4, 0, 2, 4, I'm not going to be too precise in my environment diagram. I'm just going to sort of think about it. So I'm going to for loop through this. On the first iteration, this is equal to 1. X is equal to -4. Because this is equal to 1. Because this is equal to 1, then on the first iteration, I will enter. And we said this is equal to x, which is -4. On the second iteration, x is 0. But this is -4, which is truthy. So we still enter. And we set this equal to x, which is 0. And then in the meantime, so in the first iteration, we yielded this, which was -4. Okay, so this was 1, and that let us in, and then we reset it to the value of x, which is -4. So we yield a -4. And then on the second iteration, this is now -4, so that allows us to enter here again. We set this equal to x, which is now 0, and then we yield that, so we yield 0. Now this is equal to x. So on the third iteration, when x is actually 2, this is 0, which means we skip this, and we go here. And we said this is equal to true. So on the next iteration, when x is equal to 4, when x is equal to 4, this is true. So we go in here, we reset this to the value of x, which is 4, and we yield that. So we yield the 4. So ultimately, we get a negative 404 after we list it out. And yeah, that aligns with what we did in A. It seems like when we call cut, we basically skip out on the value that follows the 0. So in this case, the 2 follows the 0, so it didn't get returned. So we got 0468. And in here, the 2 followed the 0, so we get negative 404. Okay, so now we need to do copy of paste of 0 of 3. So I'm going to draw like, I'm going to pretend A and B different happen and just reset the frame one. Doesn't really matter too much, but I know that I need to evaluate my operands first, which is why paste gets called first. I'm going to open frame one for paste, and paste has a formal parameter n, and the input to n is 0. Now let's check out what this paste function is doing. So this yields, straight away, it's going to yield that value of n. So I'm going to write out the set of values it yields. The first value is going to yield 0. And then we're going to loop recursively for x and paste of n plus 1. So this opens up a frame 2 for paste. And in this frame, the value of n is going to be n plus 1. N from the previous frame plus 1, so it's going to be 1. And this is going to yield that 1. And it's going to keep doing that, it seems. Okay. Yeah, I'm struggling to find the stopping point for the recursion, right? Mm-hmm. So paste has no real base case. So it would only stop if we ran out of values in paste of n plus 1. Okay, so paste of 0 is going to yield at 0, and then it's going to loop through paste of 1. So it's going to call paste of 1, which makes a new frame, and then it's going to yield the 1. And that will do 4x in paste of 2, which is going to yield the 2. And that yields a 3, and then the 4. When does it stop? Does it stop? I'm wondering if I should cop out and just write error, because I don't see when the recursion stops. But I wonder if I'm not thinking deeply enough. No, it doesn't error. It doesn't error. So this is an infinite generator, but that's fine because, um, for example, I can call next on an infinite generator and get the first value. As long as I ask for a bounded number of values from an infinite generator, I can actually fetch those values. The issue is if you try to list out an infinite generator, then that will error because you're asking Python to fetch an infinite amount of values. But if you ask for a finite number, which is bound by k, then that's okay. So here we're asking for like the first 3 iterations of this generator. So let's think about that. So basically, they pass in 3, meaning that this generator, we want the first 3 values in its yielding set, its yielded set. So the very first value that it yields is going to be 1. Sorry, 0, because that's the input. The second value that it yields is not going to be 1, or at least we don't know yet that it's going to be 1, because I want the generated set from frame 1. Frame 2 is not what we're looking for. Is that true? Like, is this really just 0, 1, 2? Hmm. Hmm. Struggling with this one. Let me put myself into the generator. Um, the input n is 0, and then I'm the generator. So I first yield the 0, and then I pause after the first next call. And then they call next on me once again. And then they call next on me again. So now I can resume execution here. So I'm going to try to run this for loop. However, in running this for loop, I have to first compute the result of this call. And then now I'm in the debate of, will this cause infinite recursion? Because this never returns, but that doesn't really matter for a generator, right? So now I'm really just wrestling with a conceptual thing. Like, I could be right or wrong based on just whether or not my understanding of the concept is right or wrong. And it comes down to whether or not this for loop will require this call to return all of the values, or does it just lazily for loop through the first values? Right. So if it were eager and it wanted all of the values, then this would be infinite recursion. And that is actually what my intuition believes. But based on just these problems, like I feel like it's pretty rarely error. And maybe generators are able to do this lazily and just actually, if we want the first two values, just fetch the first two values, in which case the next value, well, the first value that this generator gives us is going to be the 1. And then frame, and then we multiply it by 2 and yield out the 2 to the world. So the second value would be 2. And then what? And then for x in paste of n plus 1 means we want the next value that paste of n plus 1 produces. And the next value of paste of n plus 1 is, once again, in the next frame. Okay, so this is going to increment it to 1, and then that yields the 1, and then this will make another recursive call in which n becomes 2, and that yields the 2. So the next value that gets yielded would indeed be 2. God, awful question. um, oh, I'm on the first page. Okay, so I'll need to speed up for the rest of the exam then. Okay. I'm on the exam. I don't know. So I just have to choose one of the interpretations. And I'm gonna choose, and I'm gonna say I feel like it's rare that professor puts an error, even though my gut says error. I think maybe generators are magical and they're able to do this process actually lazily. And if that were the case, then let's ponder about what would happen then. Generators are weird. All right, so that would mean we have frame one paste. And in the first frame, n is 0. And then in the set of values, a yield is going to be the first value is just yield to 0. But then in doing so, we call frame 2. Um, frame two's n is going to be the 0 plus 1, so it becomes 1. And it will also yield it's 1. Um, but we need to get, so we have, mm, so what would the next value be? So this is going to generate a frame 3 paste. In that frame, and it's 2. And this yields the 2. So then from the perspective, so from the first perspective of frame 2, it's going to do 4x in paste of 2. But what is paste of 2? Paste of 2 is the set of values that frame 3 yields, being this. Okay. So I'm saying 4x in 2 yield 2 times that x. So the first value of x is going to be 2. So the first value here is going to be 4 because of 2 times 2. So now we've computed the first two values that frame 2 yields. And then from the perspective of frame 1, it's also going to run 4x in paste of 1. And then what are the first two values? It's going to be 1 and 4. And we multiply those two and we yield them. So it's going to be 0, 2, 8. And finally, we list those out. That is my guess. I don't know. Um, or it's just error. Okay. Complete the environment diagram to answer the following questions. Only the questions will be scored. Okay. I need to go a little quicker just because I spent too much time on that. So in global, B is 6. Log is an empty list. And then I have a make line, which points to function make line that takes a parent equals global, and then I have a shift. And then I have Z is bound to the call of shift line of make line of 2. All right. So what is the evaluation order for this? First, we have to evaluate this thing. And we first evaluate the operator that evaluates to shift line. And then we evaluate the operand. And the operand is a call expression. So I have to first evaluate that, meaning the first frame that opens up is going to be for make line. And the formal parameter of make line is A, and that's going to get set to the actual parameter of 2. And then make line says B is equal to 1. And then I'm going to list. I'm going to call a list on log. And log is this empty list. So a list says I'm going to loop through all of the elements in my input and then put those in a brand new list. So there's nothing there. So the list of log is an empty list. And to the empty list, I want to append A. That's whack. Okay, so list of log. Okay, I think log being empty is tripping me up. So let me suppose log went empty. Let's say this actually had some input, like the number 1 and the number 2. And then if I call list on it, I will get a brand new list of 1 and 2. And if I append A, then I'm going to add a new box for A and then add the 2. But the thing is, we don't actually store this into anything. So nothing happens, in my opinion. So the process is Python's going to make a copy of the empty list, and then it's going to append the 2, but then we don't do anything to that 2, meaning nothing happens. And then the return value is a function lambda of x, and it was first created in this frame, so it's parent this frame. Okay, so make line of 2 ultimately returns this lambda. And then now that the operand has been validated, we're ready to apply the operator on it. So apply means call, means that we're going to open up a new frame for the shift line function. Shift line's formal parameter is f, so I'm going to bind that formal parameter to the actual parameter, which is what was passed in for this call expression, this lambda. And I'm going to start executing shift line. Shift line says b is equal to 3. And I'm going to do, once again, log.append of b in a list. Okay. So log.append b in a list. So we have to, again, evaluate the operand operator, then the operand. The operand evaluates to, what is b is 3. So it's going to be 3 in a list. We evaluated this. And now I want to append this onto log. So log right now is nothing, but when I append something to it, I'm going to carve out a new box. And when I append an object, what actually gets added is a reference to the object. So this is the object that we're appending. So we're going to add in a reference to it, to this log in the global, because when I don't find log in here, I jump back to my parent frame, the global. I'm going to return a lambda. Lambda of y. Parent is equal to frame 2. And then ultimately, all of this has returned. All of this just returned that lambda of y. And then finally, reading from left to right, now they're asking lambda of y. They want to pass into 0, so they're asking lambda of 0. So we're calling this. So that's going to be my next frame. Y is the formal parameter. It gets 0, and its parent is frame 2 from here. And we have to execute that lambda. Okay. By the way, what is going to be the question? So they want the value of the prints. Okay. So let's try to simplify this expression. So I want to compute. I want to set 0 to the value of this. And what is this lambda? Well, this lambda was shift lines lambda, which is going to be f of y plus b. But what is f? F is make line of 2, which is this lambda, which is a lambda of x. So f is actually this thing, which is lambda of x returns a times x plus b. So if we do our algebra, so this is lambda of x, but we're passing in a y. So this becomes a times y plus b. And then we know that the y that we're passing in is a 0. So it becomes a times 0 plus b. Meaning it's just b. So this returns b. So just b plus b equals 2 times b. So ultimately, the return value here is 2 times b. And then when frame 3 wants to find b, it doesn't find b in frame 3, so it has to look in frame 2, and it finds the b here. So maybe, hopefully, this is 6. So z is equal to 6, perhaps. Okay, why there are 2 b's here? Like, we didn't actually make use of it. Okay, so when I print log, log is this nested list of 3, so it's this. And then when I print z, what I got was 6 from 2 times 3. I should recheck it. Way to go. Okay. So I'm just gonna recheck my work. I feel pretty confident about log, but I'm not sure about the second one. Or Am I sure about log? Well, log append of b, and I would just find this b. So I don't think any of the other b's get involved. Hmm. Okay, so I'm just gonna check this math thing I did. Lambda y. So this is a function that takes a y, which we know is 0, and returns f of 0 plus b. And we know b has to be 3 because it finds it right away in its current environment. So z is ultimately going to simplify to the result of f of 0 plus 3. But what is f of 0? F of 0 is this lambda. The 0 comes in, so it just simplifies to b. Oh, okay. So here's the question. Where does it get its b from? Is it the 1 or the I see? Okay. So this indeed just returns b, but we need to figure out which b. Um, mm, right. I didn't open this last frame. Okay. So we're trying to call this, that is frame 3, but in doing so, we have to call this other lambda, whose parent is this one, frame 1. And this lambda takes an x. And we know that we're handing it 0. And then its return value is going to be a times 0 plus b. This zeroes out, and then we want to find a b from this frame 4. Let's follow our rules. I don't see a b in this frame, so I'm going to look to my parent frame, and I find this b equals 1. So my return value is going to be 1, meaning that this actually computes to 1 plus 3 is equal to 4, maybe. Okay. Number 3, make tens. A list of numbers is easier for a person to sum up. It can be split into 2 groups that all sum to 10. Implement tens, which takes a list of positive numbers S. It returns true if for every positive, if every integer I, there's a positive k that satisfies. So is equal to 10 times I. Otherwise, it returns. I need an example. Okay. So saying this sums to 10. And saying this sums to 20. And the first 10 sum to 30. This sums to 10, but no slice starting at 0 sums to 20. Well, I mean, does it want us to go to 20, 30? How do we know when to stop? If for every positive integer I, where 10 times I is less than equal to sum of S. Okay, so the sum of this whole thing is 30. No. It's 10, 20, 30. So the sum of this whole thing is 32. So for every I, so if I is 0, then that's less than 32. If I is 1, that's less than 32. And I is 3. It times 10 is less than 32. So for all of these i's where multiplying it by 10 is still less than 32, Um, can you find a contiguous slice that sums to it? I need to be. All right, so I'm thinking brute force. It'd be like while I equals 0, I times 10 is less than, so let's say sum is equal to sum of s. And I have another k is equal to 0. Oh no, I'll do k is equal to 0 and I can march k forward. Um, like current sum is equal to 0. Um, and then like another loop. Current sum plus or equal s of k. And then like, all right, like if the sum equals I. Sorry, I just wrote a whole lot of things. Yeah, sometimes you think a lot of stuff on the toilet. Okay, but obviously this is not gonna like this is too slow, or not too slow, just like it's not a very clean solution, right? But I think it captures the intuition of like, all right, I'm gonna iterate while this condition is true, while I'm less than 32. And then if I'm less than 32, then I want to find a contiguous slice. I'm gonna have a contiguous slice up to a certain number, right? So that up to value I'm going to set as my k. I'm going to test all of the k's. Um, so here I'm first. So here I'm going to keep increasing my sum up to 1, up to 2, up to 3. See what I sum to, and if I sum to the current I times 10, then I'm good to go to the next I. Something like that. So let's see how they want us to do it. For x in x. So no nested loops. T plus or equal x. If something return this, if t equals okay, so this is return true at the very end. So maybe this is return false, like an early false condition, right? And like an early quit condition. So are there any early signs that okay, this is not going to be possible? Like well, I know. So something that just would flat out be impossible would be, so I'm guessing T is like summer, uh, current sum. So something that would be flat out impossible would be this, because I should be able to find I want to find a contiguous slice that sums up to 10, but I just can't find it. So here I would say t plus or equal to x, and then, well, if my t is greater than like the current landmark, and that landmark could either be 10, 20, 30, then I can just early quit and return false. Otherwise, if t equals, t equals, okay, so since t, so I want to decide, is like t like an indexer, like is its valid set like 0, 1, 2, 3, or is it like or is it more for tracking a sum? And because I'm adding on actual values from my array, then it seems like we're keeping track of a sum. Um, so it seems likely that if something happens, I want to reset the sum so I can again check for this condition. Um, I'm not immediately sure. I'm going to check what they give me and see um, if I can get any inspiration. Okay, so for G, they give me these options. If T is equal to 10, if not equal to 10, greater than 10, less than 10. So based on this, I would say greater. But how do we make that work? Okay, so I'm going to work with my assumption and see if I can create a valid solution. So let's say I choose to settle on this. If T is greater than 10, return false. Then I'm going to say if T is equal to 10, then I want to what? So T equal to 0. I mean, the only flaw here is I'm not seeing how we're. Oh wait, no, it's fine. I was confused on how we were gonna, like, this has to go to 20, right? Like the next time we're looking for 20, next time we're looking for 30. I guess I was thinking of it this way. Like, say here the sum is 100, right? Someone was like, okay, so I want to iterate from the start and find a block that goes to 10. And then if I find the 10, then I want to go from the start and find a block that goes to 20. But it seems like the way they're doing it, and the smarter way of doing it, is instead of having this amount of redundant work each time, right? When I'm computing 30, this part I already know sums to 20. And when I'm computing 20, I know this part already sums to 10. So all they're doing is they find the 10, and then they look for the next 10 starting from here to find the 20. And then when they look for 30, they don't actually have to start from 0 and look for 30. They start from the 20 and look for 10. Okay, that's way smarter. Um, yeah, if t is greater than 10, return false. If t equals 10, then I want to reset t to 0. Yeah. Here's a blank J. What is J? Oh, wait, what? Oh, okay, so what are they trying to do here? Clearly, I forgot some edge case. Oh, I just filled in everything wrong. Um, okay, so they're basically this is saying, yeah, all right. I come in, I have this running total. I don't need to look for 10, 20, 30. I can be smart and just look for the next 10. And as I'm looking for the next 10, if my current running sum is less than 10, then I'm going to keep looking. All right, that's the implicit if condition that we don't actually have to write out. If it's ever greater, then I know that I wasn't able to find a 10, so I should return false. And if I am equal, then that's good. That's fine. I don't need to return anything, but I do need to set my running total back down to 0 so that now I'm looking for 10 starting from 0 again. Now I just need to decide if I found any edge case. There's any edge cases here that I'm failing to consider. Okay, so greater than 10, bad. Equal to 10, great. I need to reset the counter to look for 10 again, and less than 10, that is the implicit condition. Then just continue looking. All right, so if t is greater than 10, what edge cases am I missing? So this says if the first digit of t is equal to 0. Yeah, I don't see why we would need a modulus, just because like okay, so let's say so we're in the case where t is greater than 10. If we're assuming that to be the correct solution, and let's say here t is 15. And here they say if 10, t mod 10, which is 5, equals 0, why would we want the last digit to be 0? Mm-hmm. Okay, so I mean, so it seems like my solution is harsh. It always just returns false. Is there an edge case in which you would actually want to return true? And why would it fall under the t is greater than 10 case? Um, if the current sum is 15, hmm, when would we ever want to return true? Let's say this was our list. 30. Now let's make it more interesting. So first at 10, and then it has 20. So on the first iteration, we don't trigger this, we trigger this. And t is equal to 10. So t gets reset back to 0. And then the second iteration, we go in and add the 20. So this becomes 20. T is greater than 10. And I would want to just return false because If sum of S mod 10 equals 0, the sum of S. Of S mod 10. So they're saying if the sum is like a multiple of 10, then I would want to return true. I'm not sure if I agree with that. Hmm. So look at the second example. Here, becomes that first 10. So then we set to 0, and then we start looking for the second 10. So we get the 6, and then t becomes 8, and then t becomes 14. And then I just want to return false. I don't feel like there's an edge case. Can't find it, so I guess I'll just leave false for now, but I could be wrong. Implement the counter class. A counter has to count the number of times inc has been invoked on itself or any of its offspring. Its offsprings are the counters created by its spawn method or the spawn method of any of its offspring. Count how many times inc increment has been invoked on itself or any of its offspring. Um, what? Oh, am I going to finish this sometime? Okay, I think I need to like sprint to the scheme stuff. Yeah, time is not looking good considering I only have until 3:27. So I have under 2 hours left. Oh wait, so I've taken a bit more than an hour to do the first 5 pages. So I need to sprint. Um, a counter has a count of the number of times increment has been invoked on itself or any of its offspring. So here we make a counter, and then we do total.spawn, which are the offspring of total. Let's say I have total and it has offspring, odd and even. And then odd is going to spawn 1 and 3. And then for C in all of these people, 1, even, 3, even, odd, even, I'm going to increment them. Okay, so 1 gets incremented, even gets incremented, 3 gets incremented, even gets incremented, odd gets incremented, and even gets incremented. There's 1, 3, 1, 1. And if we get each of their counts, it says that a counter has the count number of times it has been invoked on itself or any of its offspring. So total, it should say the 1 plus 3 plus 1 plus 1, which is equal to 7. But it says it's 6. Yeah, because 1 plus 1 is 6. Okay. Okay. Okay, so in a counter init, it has a parent which gets set. And I noticed that when we initialize a counter, we don't set the parent manually. So it seems like in here, we have to configure the parent. That's going to be our responsibility. And then it seems that here's empty. I mean, I think for a counter, we probably want to count and we make reference to it here. So I'm going to say, seems logical to me that a counter will have its counter start at zero. When I increment it, I have to increment my own count, but I also have to increment all of my ancestors' counts, right? So I know total has a count of seven. So if I am three and I increment my own count, then I have to make sure my count gets propagated up. And then spawn. Okay, so I should probably work with spawn first because I noticed that this is the first method that gets called. So I'm assuming this spawn is what sets up the parent relationship thing. So spawn seems to be like how I birth children, right? So how do I birth a child? Um, I am in counter and I want to birth a child. Um, so I need to return a new counter because that is how we make new instances. And what does a counter take? Well, it takes a single argument, parent. Okay, so when I make total, I don't need a parent because it has no parent. It's the root. But then when the parent wants to spawn new ones, it has to likely specify its parent. And who is the parent of my children? Well, it's me. And who is me? It is self. Self is a pointer to this current instance. Okay, is B and C. I'll take some inspiration from here. I'm going to fill in the counter of self. Yeah, this thing would be infinite recursion. I'm going to take inspiration from here and see what suggestions they have for me. I'm assuming it's recursive. When I drew this out, it felt like tree, and it felt like a tree, right? Um, okay. So as total, when someone increments me, mhm. Okay, so as total, when someone increments me, I don't have to do any work. But if someone increments three, then I basically have to make sure that all my ancestors get incremented, invoked on itself or any of its offspring. So now we have to put ourselves in the perspective of an offspring, and we have to increment all of our ancestors. We have to increment even. No, it doesn't seem like it. We just have to increment everyone along. This path, like these two people. Uh, Wait, what did we increment again? We incremented one, one, even, three, even, odd, even. So the total for odd should be two. Is that true? No, it's three because because why is it three? Oh, because itself it was incremented once and has two offspring that incremented once. Okay. But in terms of the three, it just so the one and the three both have to inform odd that like you only have to inform upwards. So even though it's a tree structure, from the perspective of a child that is alerting its parents, it's a linear path. Update this and then update this. So we're kind of I can imagine that I can just for loop up my parent pointers. So kind of like when you do like a frame lookup in your scheme project, right? We can kind of look up our parent like while self parent self dot parent. I can do this, or I could do something recursive. What do I want to do? So I can't do an if because there might be multiple parents. I need a loop. This just that will error. Parent does not exist, only self dot parent exists. And do I want to just increment my parent, or do I want to inc p plus or equal 1? So I don't want any solutions of p because we already know these aren't true. So I can just block out all of these. Parent doesn't exist. Parent doesn't exist. Only self dot parent exists. Um, count as an int. It doesn't have an inc function. Parent is not an int, so it can't add one. So it can only be these two. So at this point, we've narrowed it down to 50-50. So do I want to? I mean, I think this is fine. I don't see any reason why this doesn't work. Mm. Oh, no, while self-dot parent doesn't work. Because if I want to do while, like from the scheme project in the frame lookup thing, right? I can either do I can either do while parent plus or equal 1. But then in the next iteration, I have to update parent. Or so let's say I have parent equals self parent. And then here I have to set it to or okay. Um so I'm being unclear. But the idea is if I use a while loop, right? I actually need another line here that allows me to update the value of what I'm checking here. Because they don't give me an access to another line, then I know that I can't work with that and I should instead go with recursion because if I do it recursively, then I just need one line. So instead of worrying about while looping all the way up, I'm just going to abstract that recursive lookup process recursively. And again, intuitively, I want to go iteratively. I want to use a while loop, but I saw that I only have one line, and I know that with just one line, uh, that won't work. So I can just do the if solution. And if my parent is not none, then I'm going to recursively say self.parent.inc. And that will recursively bring me up the parents. Um, Although I struggle to see why, I feel like both of these could work. Like this is kind of redundant because each time the while loop would just run once, but it feels more correct. Show on time. Implement the misdict class. The misdict has a dictionary ID. It's a get method, takes an iterable keys, returns a list of all values in D that correspond to those keys. and counts the number of keys that did not appear in D, called misses. Um, okay, so a misdict has a dict, and it gets a list of values for. Okay, I'm gonna see an example. So double maps 1 to 2, 2 to 4, and if I do get, I get 1 2, and I get 3 6, and I get 5 10, and I get 2 4, but there is no 8, so we have one miss. So we have one miss, three miss, two miss. So we have six total misses. Um, oh no, our double has four misses. So when you print out double, it will report that it has four misses, but it also has to know about halves misses. So why would half know about doubles? For any. So every mystic needs to know about every other mystic. Hmm. Okay. So misses uses a counter. Okay, so immediately I'm able to implement this tree structure out of the box. But how does that even help me? Um, I'm not sure. I pull my nose. Okay, I have an idea. Um, so like, how do we use this tree structure? Well, from the first one, I remember like the top guy has a count of all of the children's counts, right? So somehow, um, when an instance needs to report the total misses, it can refer to that the misses that are tracked by the root. So every single instant needs a reference to the root, which I think is what this is. So that's why this is a class attribute. For the mystic class, it has a single root counter instance. Uh, Okay, so that's going to be the intuition. Let's first implement this get class, which just seems to be retrieving from a list of keys. So for k in keys, if I have that key in my dictionary, then do I just I get the value and then I append it to my dictionary. If it exists, then I can safely index into it like that. Otherwise, I need to track that I missed. Oh, so here I can spawn, right? That's how I form my tree. I see. So instead of this tree, what it looks like, it's gonna look like this. Right? Everyone spawns as a direct child of the root misses. So it'd be like this. Uh, can I do this? I mean, this is just wait, missed it is a class. I cannot return a yeah, I can't pass a class in. Does this work? Yeah, we're just specifying the parent. I mean, this is, we're just re-implementing it. It's, not as clean, but I suppose it's possible. And then otherwise, I want to report uh, my own misses. So I'd hope that's just a number. Wait, no, it's a count. It's a count. It's a count. And then the counter counts. So I could just increment. Okay, there we go. So misses increment. And I know that when I increment, I will also alert my parent, which is this root guy. So everyone's going to increment themselves, but they will also alert their parent. So ultimately, this fraction is just going to be seems to be self. This is it's the count. Is it just not count divided by the root? And then what is G? G is incrementing my own misses, which also alerts my parents' misses. Mm, no, I want to use ink because that will alert my parents, and I need the self. Uh, Here, I just want my own misses divided by the parents' misses. What's the difference between these two? Um, oh, it doesn't actually want, does it? It doesn't actually want the fraction, it just wants to, it doesn't want the actual value, it just wants the fraction. So we do need to, uh, we need this to display as a string. So we need this. Mm, okay. promotion to, I'll be back, sorry. Okay, promotion to 61B, given a sequence S and positions I and J. Promoting an element to I from J means reordering S so that the element originally at J is now in position I. All elements originally positioned between I and J increase their position by index by 1, and all other elements stay where they are. Promoting to 2 from 4. Okay, so J goes to I? Yeah, J is now at I. So 2 from 4 would mean moving 4 to 2. So it's this one and this one. So the 150 goes here. Which means all of these guys have had their index increased. $30, $60, $150, and then does everyone else just get pushed forward? $30, $60, $150, $90, $120. Okay. But don't mutate S. Okay, so if this is the input list S, then I would want to return okay, so this is I and this is J. So first I need to return is this, because that doesn't change. So I need to go up to I. And then I need to promote and stick J in here. So I need to add S of J as a list. And then everyone else just gets pushed back. So it's just going to be S of I. Um, oh, but here I have to take out the J from this remainder section, meaning this isn't just S of I, it's up to J. And I'm just going to slice out that J by skipping it like that. Okay. So S up to I, this is good. And then we S of J in a list, which is the same thing as, oh no, this is, list has to take a list, and this is not a list, so this would error. S of J to J is the empty list, right? If you index a list that's this from 0 to 0, that's, you're getting nothing out of it. But if you go from 0 to 1, you would get this 4 in a list because it's a list slice. So that's totally fine as well. We want the output to be a list. So we have this guy, and then we want I to J. So we cut out that J. Actually, no, this doesn't cut out the j just yet. It's up to this j plus 1 to really cut it out. Implement promotions, which takes two lists of numbers s and t that have the same elements, possibly in different orders. It returns a minimum number of promotions that must be applied to s, so that has the same order as t. What returns the minimum times promote must be called to start from s and return t. Okay, so we want to get from this s to this t somehow. And in order to get there, I want to promote index 2 to the 1. I'm just going to draw this out. We have 2, 4, 6, 8, 10, 12. And the first promotion is I want to do this. So that does 2, 6, and everyone else gets pushed back. And then it says 2, 3. So this. And then finally it says 4, 5, which is 0, 1, 2, 3, 4, 5. And then does this match this t 2, 6, 8, 4, 12, 10? It does. Okay, so we're just iteratively finding the shortest way to do this. So this seems like tree recursion because I want to consider all of the possible ways to do it. No promotions needed. It's most likely our base case. So if they're equal, then I can just okay. So how do we want to do this? So I'm starting from here, and I want to consider every possible promotion, right? So of course, it turned out, so a promotion must be between a set of indices, a set of adjacent indices, which is a finite number. So for this given list, right, there is a finite number of adjacent pairs, being it'd be 0, 1, 1, 2, 2, 3, and so on. So we want to consider each, and then we want to try, and then for each of those promotions, we want to try it and then see if it gets us where we want it to be. And then here it seems like we're going to make progress by doing by chopping off. So how can that help us? So they have the same elements. They have the same elements in terms of minimum, and they can have duplicates. Can't have duplicates. Okay. I'm trying to figure out if it's true that if two elements are equal, then I can just consider and chop them off and consider the rest. And that's how we implement the recursion. But that seems very natural if I know that all the elements in the list are unique. But is that true if there's duplicates? I don't see why it wouldn't work if there's duplicates. Yeah, right. Like if we find a match, then now we're fine to consider the same recursive subproblem on the rest. Which I assume is what's going on here. And yeah, so if equal equal, so no promotion needed, equal equal, no promotion needed, equal equal, no promotion needed, and hit the base case. So maybe this. Sorting wouldn't work unless we sort both, right? So, and then just checking equality Well, if they're equal, then we wouldn't need recursion. So this is not. Uh, so now we need to consider E and F. Okay, let's get to it. So now we need to actually do promotions. We're taking a min and we want considering every possibility. So we're taking a min over what? So they're saying 4j in the range of 1 to n of s exclusive. If something, then I want to do something. Then I want to compute the promotions of something. So I need to figure out the if what, then find the promotions of what. Do we get any help? Yes, we do. We get help here. So these are the possible if conditions. Um, if s of 0 equals t of j, if s of 1 equals t of j, if s of j equals t of 0, if s of j equals t of 1. Okay, so let's first figure out what are we iterating through? It's this j that's iterating through, yeah, s, the first list. Okay, so I'm running a for loop through this first list. So that's the only thing being varied, my current position at this list. So look at the 2 and then the 4 and then this. And then, okay, so we found a match here, right? So now we're in this case. My j is going to start here at the 4. And then I mean, I don't understand why we would. Are these identical? Just one is 1 and one is 0? I mean, I don't really see why we would ever consider care about the first index. The second index instead of just the first one. Okay, and we're just iterating through S and seeing if we can find a value that is equal to t of 0. And if so, then we want to try to promote that. And then, sorry, I that was only for this first. I made an incorrect statement that I can only make adjacent promotions, right? I can promote from anything to anything. But it seems we're going to be smart and only consider that promotion if I'm first, like, actually show that they're equal. Because I don't want to just try every possible promotion. I want to make sure ensure that that promotion actually contributes to building out equality between these two lists. So do I want S of J or do I want T of J? Well, I notice here they have T of 1. Mm-hmm. Mm-hmm. We first have 2, 4, 6, 8, 10, 12. And then we have 2, 6, 8, 4, 12, 10. Well, in the first frame, we observe that these are equal, so we don't even have to exhaust a single promotion for that. Here, we see that they're not equal. And I actually just noticed that this range is not from 0. It starts from 1. So does that change things? Why would I want to start it at 1? So instead of iterating starting from here, they actually start from here. Yeah, which I guess makes sense. Um, because I guess this is like the set of promotee indexes, and this is the candidate position to promote to. So I don't need to consider this position because um, well, I already know that like the only reason I'd want to promote the 6 to a 6 if is sorry, the only reason I'd want to promote something at this index to the same index is if they're equal, but I know they're not equal because I already failed the first check here. Or just like, yeah, I wouldn't want to promote something to the same position. So I should only consider at an offset. So I should start at 1. Okay. So the range starting at 1 does make sense to me. And then if I find this match, which I am comparing against the 0, but now I need to figure out which one. What do I do? They call promotions on T of 1. So they end up calling recursing on this chunk. And then what chunk of S do I want to recurse on? I noticed they got rid of the 6. So I think, do we recurse on this? Like this, so we make progress like this. Yeah, that seems reasonable. So it's like in the CATS project, right, where you're kind of computing minimum mutations. What you're going to do is um, you make the mutation and then you consider what's left after you make that mutation. So here, the actual mutation that needs to happen is this promotion procedure in which these get swapped. And then we want to recurse on what's remaining. So we did one promotion and then we want to continue computing promotions on what's remaining. So we want to the S that we want to recurse on is okay, so T. So this position in T, being T of 0, is the position that we're promoting to. But this is the target position to promote to. And if I'm able to find something that I can promote there, then I want to iterate. Let's say I find this and I want to promote it there. Well, what do I need to do? I need to pull this out. Well, let's not make it at one of the ends. Let's say it was here. Then I need to actually iterate. I need to recurse on this. So I need to recurse on everyone but that thing because I'm pulling it out because I'm promoting it to this position And then once I promote it to that position, it won't actually make it into my recursive call. In the same way in minimum mutations, you don't actually like you consider the possibility of adding a character, but you don't actually need to make that addition because on the next recursive call, or you count the fact that you make the addition, but you don't actually let it mutate your result. Super unclear, but maybe made sense to someone. Apologize. So J is the promotion index. If I find a place to promote that, then I need to chop off that J. And both of these are going to be the same length because here we chop off one item and here we chop off one. Okay. Implement promote link, which takes a link instance and two non-negative numbers. It mutates S by promoting I from J and then returns S. Okay. Implement promote link, which takes, okay, so we're just doing the promote thingy, but now with a linked list. So how do we do that? It is a recursive function. Is it recursive? Oh no, it's not recursive. It still could be recursive, but I'm not sure. Okay, it doesn't seem recursive because we kind of segment out I and J into two different workflows. So this handles the I part, this handles the J part. So if I have a linked list of 1, 2, 3, or let me just make the values the direct indexes. And let's say I want to promote this to this. Or no, this to this. Well, first of all, like I start off at the head of my linked list, right? So currently, nothing interesting has happened until I even hit I in the first place. So if we're not even at I, if I is greater than 0, is this multiple assignment for G or no? Where is G? Oh. Then I need to move along. Nothing interesting has happened yet. So like this problem doesn't even matter to me. Like this 0, I don't care about you. I only care about the case. Or it's just like I'm kind of lining up this linked list so that I'm pointing right at the start, right at the promotion index. So if I is greater than 0, then I just want to skip forward. And I can do that by recursing. Just feels really weird. S.rest, which lets me skip forward. And then if I skip forward, then my I also changes. So before here, from the context of my whole linked list, my promotion index I was 1, right? But when I chop off the first one, now it's 0. So while I is not 0, I'm going to keep chopping. And I have to decrement I to reflect the fact that I'm chopping. And I think, yeah, J also has to change because the length of the list is changing. So the indices I and J must change to align with that. Once I've set it up so that my I actually points to here and my J points to here, now I'm ready to do my insertion. So it seems like I'll definitely need one pointer to keep track of this value. And then I'll probably need another pointer keeping track of this value. And then I'll just need to do some linked list operations. Like what I'm going to do is I'm going to move the 3 to the front of my list. And then I need to set the rest equal to like what used to be the head. old head dot res, something like that. Okay, so this aligns the problem so that the insertion index is the start. So this just makes the final um, cutting apart of the linked list like if you're inserting into an index, um, no, this not gonna say anything. Okay, so now we're in a scenario that looks like this, and they have an insert and they have a tail. Insert is going to point or is going to get set to this value. And then tail is going to point to s.rest, and s is going to point to the head. And they're saying while j is greater than 0, so we're iterating up to j. And then tail and j get changed. Mm. So right now I is 0. I'm debating if, okay, let's hypothetically say I is 0 because we decremented it down. And then j is like this too. So the dream scenario is we want to do this promotion. 3, 2, 1. No, that's not true. It's going to end up looking like 3, 1, 2. But do we want the I to be 0? I'm thinking. So I need to fetch the value here. And I need to insert it at I, which I know is the start. And here I need multiple assignment. Why would I need multiple assignment? I need some hints. So I'm going to look at I and J. And here I'm going to set something to insert. And then finally, I'm going to return J. So insert right now is a first. So it wouldn't be a linked list. So I'm setting something to a number, which means this should also be a dot first. So it should be s dot first, s dot rest dot first, tail dot first, or tail dot rest dot first. Still just do not get why we need multiple assignment here. Hmm. Hmm. Let me make this link longer. Okay. Okay. So insert should probably point to the value that I want to insert. So I need to get insert to be this 3. Um, so I think H here, I should probably be setting insert equals whatever the current value is. And then what's going to point to the head of my linked list? Well, that would be S. So maybe I can set it to S dot first. And then I guess, simultaneously, I guess I can set S equal to S dot rest. Do I need to do that? No, I already have tail. So I don't need S. I can just set it to tail dot first. Okay, so if I do this, tail currently is set to here. I don't need to set it to the start because I know that this is the place I'm promoting to. So I wouldn't promote 1 to 1, right? The first value that could be promoted to me would be the next one, which is why tail is going to start at s dot rest. And then, so here I set insert equals tail dot first. And then I move tail along to the next value and I decrement j to be 1. And then I set insert to be this value, just 3, and then I decrement. And then tail moves forward and I decrement j to be 0, and it's no longer greater. So now our code has stopped. Okay, so at this point in time, I know that my insert value is 3, and tail points to the first value after that 3. All right, so what mutation do we want to make? It seems that I want to replace the 1 with the 3. I don't really want to replace it. I kind of want to add it forward. Because if I add it to the front, then I don't have to mess with the 1 and 2. Whereas if I replace this 3, then I have to kind of propagate everyone down. Which is simple in my case because there's only 4 elements, but you can see that that could be very cumbersome. So I want to kind of stick the 3 in the front. So how do I add something to the front of a linked list? So I can do link of the insert value. And then everyone here being, and what is that? Well, that is s dot rest. But what is tail used for? Well, I think we probably have to use tail to snip off this 3 value. And how do we do that? Well, I want to set 2's rest to be the tail. So arguably, we do want to turn the link of insert and tail dot rest. Would it really be tail dot rest? Because now tail's pointing at the end, right? Because tail, okay, so if we're assuming that this is correct, where I want to return a link of insert and s dot rest. Well, so what does tail point to? It points to the first element after the insertion of the promotee points to here. Okay, so what do we return? We return a link of this 3 and tail, which right now is only 4 or 5. That's going to be problematic. Hmm. Should I come back to this? Yeah, I'm not doing well in time, and I'm missing something. So I should probably come back to this. Uh, okay. Fresh produce, implement products which takes a tree instance t with positive integer labels n, positive integer labels and positive integer n, returns true if every path from the root to t has labels that equal n when multiplied together. One, two, three, and 6. So this multiplies to 6, this multiplies to 6. Um, but it will not go for 12. Okay. Um, so if I only hand you a single node, like 1, then the only way for that to equal the n is if it equals the n. So I just want to return if t that label is equal to n. If something I want to return false, else I want to return, they're going to make us do some list comprehension. Um, if what? Okay, and then I also know that if my okay, yeah, this doesn't make this. I don't think that makes sense. But if I know that if my current label is greater than n, then since it's positive, I can't like if this is 100 and I'm trying to multiply to 6, then if this is greater than 6, then I immediately should just quit because I can't. If I multiply myself, I'm only going to get bigger. So I should only recurse if I have a nice little 1 here that I know can grow and become that 6. Uh, okay, then I want to do this recursive call, and I'm going to use the recursive loop of faith. So I'm going to say if I make this recursive call on this, what will that return to me? If I do products, uh, this B, mm, 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 mm. I see. Okay, so from the perspective of, so I'm at the root. Um, and then these numbers don't make it the most clear, so I'm going to change them. It's going to be 2, 3, 4. These multiply to 24, so this must be 12. Okay, so and then n equals 24. From the perspective of the root, if I want all of my paths to sum to 24, then I want all of my subtrees to multiply to 12, right? I want this to multiply to 12, and I want this to multiply to 12. Because if they multiply it by 12, then I know that once they're multiplied by me, then they become 24. So that is what I want out of my branches. So for each of my branches, I would want my branches to ultimately form a product of 12. And how do I get that 12? Well, that is my total n divided by the value that I am, which is t.label. Informative? I'm not sure. And then I want all of my branches to sum to that. So all I'm going to do is all of products of B for B in PR branches. And I want that. I want this condition to be true for all of them. Sub-branches. An increasing sequence is a sequence of integers in which each element after the first is larger than the previous element. Implement produce, which takes a positive, it returns a tree in which the product of the labels along every root to leaf path is n. Every increasing sequence of integers starting with n that has product n as a root. Okay. I want to return the largest tree. I'm returning a tree. I take a number, and I want to return of all the trees in which the labels for every root to label path are increasing and have product n. I want to return the largest one. Damn. Okay. Not good, guys. Okay. So what is this tree? Yeah, the output tree they produced here has 1, and then 2, 3, 4, 24, and then this 2 has as children. Wait, what is going on here? Okay, paths are 1, 2. Oh no, I messed up. 1, 2, 3, 4. 4, 1, 2, 12, 1, 3, 8, 1, 4, 6, and 1, 24. So 1, 2, 3, 4, 24, and then 1, 2, 3, 4, 1, 2, 12, 1, 3, 8, 1, 4, 6, 1, 24. Okay. So this is the largest tree where everyone. Oh, yeah, this is 24, not 12. Okay, so everyone multiplies to 24, and all the paths are increasing because every number is larger than the previous. And they want us to order the result in every sequence of siblings. Nodes with a common parent is an increasing sequence. put the siblings in increasing order. Okay, so these siblings must be increasing. Okay. Pick a number and you want to produce a tree. Hmm. Okay, so if the target is 24, then I guess what we want to do is we want to iterate through all of the divisors of 24, being 1, 2, 3, 4, 6, 8, 24. And for each of the divisors, do all the trees have root 1? Um, I guess. So for all of these numbers, take the 24, and I take this 2, and I think about, I don't know, it seems like a factorization problem. Okay. I'm going to need the skeleton to help me out for sure. Okay, so grow. It's going to take a tree. That's just one node. It's going to take an n, which is 24. How the hell do we grow to become that tree? Well, I want to, I guess, iteratively add branches, right? So the first branch I want to try to add is this 2 branch. And I only able to add it. Yeah, so first of all, how do I get through divisors? Or k in range of x plus 1, where x is what, the target? Yeah, so x is the target. So I want to iterate all the way up to 24. And I don't need to count 1. So this is how I'm going to get the divisors. Okay. So if the 24, which is our x. So on the first iteration, k is no, 2. On the first iteration, k is 2. Okay. And then what is the question that we ask? Well, first of all, we observe that that 24 is divisible. And then once we do that, what do we have to do? Well, I know that the remaining product is 12. Oh, so then we can recursively, so then we want all of the branches that grow to 12 in order, but that's just the recursive subproblem, right? Like these are all of the ones that multiply to, no, these still multiply to 24. But these have a root of 2. Oh. So these are all of the like we see that this is the largest tree we can grow with a root of 2, and that um form paths to 24. And then these are all the ones with root 3. So it doesn't like, so when when we're going to recurse, I don't want to start my next one at 2. I want to start myself at whatever my label is. And then so what is this branch? It's going to be recursive call. Grow of, what a cool problem. And we're still trying to get to 24? Yes or no? Probably not. Like we have to chop it down by whatever x is. Maybe all of these. Yeah, right. Because these only have to go to 12, and then this only has to go to 4. Um, if what? If what would we want to add it? G. Oh, that's the only one we don't get. That sucks. Grow tree of x. Grow tree of x and x. And not n for div x, uh, but x for div k. What is e? What is d? No, it's the only one we don't get. So branch right now is a tree. If what about the tree? Mm, what condition have we not enforced? So I think because we're doing it sequentially, we do the increasing thing. Um, it's 3 points. So awful. Um, product is n. Yes. Every increasing starting of fun is a root to leaf path. And every has to be increasing. That's true because we're iterating upwards. Mm, I don't know. What could possibly go there? Not sure. A pair of schemes. Implement the scheme procedure all pairs, which takes a procedure f and a list s. It returns true if f of x of y is true for every pair of adjacent elements x and y and s. Uh, it's x plus 1 equals y. So x plus 3 plus 1 is 4, 4 plus 1 is 5, 5 plus 1 is 6, and so on. Okay. So here we just want to iterate in pairs. I want to first grab the first two elements, call f on them, and see if it returns true or false. If it's false, I can early return false. If it's true, I want to keep looking. And if my list is emptied, I want to return true. Um, or so if S is null or the cutter is null, oh, what? I thought it'd be if not. It could be like if s is not nil or s dot rest is not nil, then do something. But they're saying if s is null, I don't know. So what would A be? So A, we have to apply F on the first element, which is the car of S, and the second element, which is the car of the coder of S. And then if that's false, then we early return right away because we're inside an and. And otherwise, we just recurse on the next two. So it'd be F on the coder of S. Um, but not on the coder of S because we want to like after 3 and 4, I don't want to check 5 and 6. I want to check 4 and 5, which is we want to iterate on the coder of S. Mm. No, sorry, not this one. Okay, well, okay, so this is not syntactically correct, right? This has to be whatever the answer has to be. It has to be one single bubble because and or no, that's not true. It doesn't have to because and can take is variadic, but like and can take a lot of arguments, but this is not proper syntax. We're not calling it. We're not calling it. We're not calling it. We're not calling it. Here we're calling it on the list instead of the first element. I don't remember why this. Yeah, I'm gonna guess apply does the same thing. Hopefully, I have no clue. I don't remember what apply does. Maybe it's on the cheat sheet. I don't have it. I don't have access to that right now. Um, which takes a list S and returns a list of every pair of adjacent elements. So return 3, 5, 5, 7, 7, 9. Okay. So definitely want to show pairs on Twitter or not. Mm-hmm. Okay. So let's say I'm here in a list. What do I want to do? Well, I want to put these guys in a list. And append this onto the recursive call. This onto whatever the recursive call produces to me. So I know by the recursive leap of faith that when I recurse on this, by the recursive leap of faith, this should return to me 5, 7, assuming correctness of my function. And then all I have to do is append my 3, 5 onto it. So now the question is, do I want to append it on? Do I want to list it on? Do I want to cons it on? Well, if I append it on, then what's going to happen is I will get 3, 5, right? This flattens it, so I no longer have this pairing. So what I actually want to do is I want to count it to make sure that the 3 and 5 are still nested together. I'm going to A, I'm going to cons, and then B, I'm going to the car of S and the car of the coulter of S together in a list. There's probably many different ways you could have expressed this, but this seems the easiest to me. And then I just recurse on the coulter of S. What order of growth describes the time it takes to execute unpair of S in terms of the length of the input list? Assuming that car, coulter, cons, and L are all constant. Um, sorry, I kind of just flew by these. I didn't even really look at the base cases. To be honest, I just kind of assumed the base cases would handle the base case. Yeah. But I'm very short for time. So I think that's like a valid heuristic you can do during exams. It's risky, be careful. But don't be as rushed as I am. Take care of your time. What order of growth would it take to execute unpair of S in terms of the length? Okay, so I'm assuming unpaired just takes pairs and it mashes them together. Um, so just intuitively, it's probably linear because they just have to iterate through the list once. Like if the input list grows by one, then we have one extra unpairing. And I'm assuming that the unpairing itself is a constant amount of work. But okay, so this doesn't really matter to us. Uh, this doesn't matter to us. So otherwise, so I'm assuming that the input looks like this. I'm not actually sure yet. But let's see if this does what I'm thinking it does. I'm gonna cons the car of S, which is the one, onto which is the one, onto unpair the clear of S. But what happened to the two? Hmm. I think they should be linear because regardless of what's actually happening, um, this function or as many this function will run for as long as coulter of S. Like coulter of S is sort of the limiting factor that's deciding how long this recursion will go. If S is 100 long, then it will take 100 coulters to get to the end to hit the base case for the function to end, right? So because each time we're stepping by one, then with respect to the length of S, if the length is 10, then it'll take us 10 one steps. So I'd argue it's linear. Implement the scheme procedure. Arcane jobs. Okay. Go P. I'm going to do the sequel. And then I'm going to try this data, programs as data. Whoops. Oh God, we are back with 20 minutes on the clock. Okay. Um, Arcane jobs. We want to make a list of people living in regions it governs that have unique jobs. Create a table with columns labeled name. This is what we want to make. Contains one row for each person living in a region governed by the council, who is the only person with their job among everybody living in regions. By the council. Okay, so the who table has a bunch of people in columns for their name, where they live, and their job. The gov table has one row per region and columns for its name, for the place, and the group that rules over it. Okay. So between these two tables, how are we matching? So it seems like the column that we are going to join on is this thing. Um, that's sort of the link. The who. Okay. All right, so let me reread this. Wants a list of all the people living in regions it governs that have unique jobs. Create a table of columns labeled name and job that contains one row for each person living in a region governed by the council, who is the only person. Yep, do we only care about this? So for each person living in a region governed by the council, they have a string, so I'm assuming this is a constant value, who is the only person with their job among everybody living in regions ruled by the council. Okay, so of the regions ruled by the council, I want um, the people who are the only people that have that job among everybody living in that region. So of the people that live in a region governed by council, return people who are the only person in their region to hold a particular job. Okay. Um, so so this is going to be the complex part. Only person in their region. So I'm looking for like the key part is in their region, right? So among their regions, I'm going to need a group by region. Um, and then they're unique if that group is size one. Um, Something like that. And I'm gonna take from um, who, comma, gov, who as A, gov as B. And the way I'm going to join these tables is, where a dot region is equal to b dot place, and um, that place is ruled by the council. B dot ruler equals council. Uh, and then I'm going to, of those rows, no, not in their region, in their job, right? Among everybody. So we're going to group by job. From this, we have this um, where a dot region these are all possible, right? um, oh, do we need a self join? We need a self join. So when we join this onto this, what we get is a table that looks like council. Council. Okay. And then from there, we get a table. Each person living in a region governed by council is the only person with their job among everybody living in regions. So to me, then we just want to group by their job. And if they are, I don't think we need a self join. I don't think that provides us any new information. We don't need to compare any of these against itself. So because we don't need the aliasing, I think we could just the region equals place. And ruler equals council. See. Um, let's see. Am I allowed to have group by and having? I don't know. Sure hope so. Makes sense. Implement the scheme procedure all pairs, which takes a procedure name and a list as it returns an and expression that calls the procedure name divide procedure name on every adjacent pair of element and S. Assume show pairs is implemented correctly. So what will this do? This will do. So we'll. Okay, so I need to stick an and in the front, and then I need to tack on. I need to call show pairs on this to get all of my pairs like this. And then I need to stick on ink right in front of it. And this looks similar to that discussion problem, like the or discussion problem from the macro one. So for this, I just want to map. Okay, so at the very front, I want the and. So in order to, so this is the expression I want to construct. And in order to construct it, I need to stick an and in front. I don't want to append it because if I append it, then I will again lose the nested structure. I think. Yeah, so here I'm producing the expression that once evaluated would produce this. So in order to do that, I need to cons quote and because I don't want to evaluate the and yet. Um, and then B, I just want to map lambda. I forget the syntax for lambdas. Um, yeah, I forget the syntax for lambdas. Guess I'm going to look up the cheat sheet. Resources, links, guides, final study guide. The syntax. Okay, so it looks like lambda. And for each of these expressions in the pairs, or I would just call it pair, for each pair, I want to return the procedure in front. And we get the procedure as a name already as a unevaluated. And since this is not a defined macro, this is just a normal procedure. So when it enters the macro, it will get evaluated. So it loses the quote, which means we need to give it back the quote. So it's going to look like cons. We want to, oh, this procedure name. How do I do that? Is the procedure name onto the pair, maybe? Okay, so this takes a pair, like 1, 2, and what does it return? Where procedure name comes in as an unquoted, as a quoted, something like this. Um, and that will get evaluated. Okay, so if I just cons it right away, um, we need to get the quote in it somehow. So if I don't do this, right, what are we getting? We're getting bouncing this onto, oh no, right now this would be just this, which is bad. So I need to do parent list. This. But no, I need this quote. How do I get that quote? Um, mm, hmm. Is it quote proc name? Hmm. Hmm. Everyone comes in for quote. It enters the macro, and then it gets quoted again. So that procedure name is bound to um, is bound to an unevaluated ink. And we want, how do we keep it unevaluated? I'm just blanking. Probably out of time. Well, that sucks. Um, yeah. Yeah, definitely something checking with the label. Um, yeah. Oh, time is up.